people say, "Oh, evolution did that," or natural selection did. Natural selection doesn't make anything, right? You have to have the changes to get a new system that, okay, maybe get preserved. Okay, that's different. But natural selection doesn't make anything.
ID the Future, a podcast about evolution and intelligent design.
In a universe of non-living space and matter, life is extremely rare. And in order to stay alive, humans and other organisms have to overcome a myriad of engineering challenges. Just how is this done? And more to the point, is an evolutionary process capable of producing the solutions to these many challenges? Welcome to ID the Future. I'm your host, Andrew McDermott. Well, today I conclude my conversation with Dr. Howard Glicksman, co-author with engineer Steve Loftman of the new book, Your Amazing Body. The book is a fresh, abridged version of their previous book, Your Design Body. Dr. Glicksman has been a general practitioner and hospice physician for decades. He's now a consultant who mentors hospice physicians in the management of fluid overload, especially due to heart failure. He received his MD from the University of Toronto. Now, in part one, we set the stage by discussing how Dr. Glicksman's qualifications and his experience as a physician prepared him to write this book. We also looked at the fruitfulness of bringing together an engineer and a physician to explore how the human body overcomes the many challenges it needs to stay alive. Today, we're going to dive into examples of those challenges and solutions, and why Darwinian evolution cannot adequately explain how life prevails against the odds. Let's get back into the conversation now. Now, in the book, you quote biologist Michael Denton saying, between a living cell and the most highly ordered non-biological system, there's a chasm as vast and absolute as it's possible to conceive. In other words, life is set apart from non-life in many dramatic ways. Now, you unpack some of the ways in this book, Your Amazing Body. One of those ways, one of the challenges of staying alive, is maintaining a separate and distinct equilibrium from the environment around us. The fancy word for that is homeostasis. Now, why is this important, and how does the body tackle that challenge?
Well, homeostasis is basically you need to maintain this equilibrium. So, in other words, the cell, first of all, has a cell, and this is at the cellular and the total body level. So, if we're talking intercellular processes, let's just quickly look at the cell. You don't have a cell membrane. You don't have any integrity. Everything falls apart. The nucleus, proteins, everything flies about. So you have to have a cell membrane, and that encloses the cell. And the cell, in order for it to function properly, it has to have the right amount of proper volume, and it also has to have the right chemical constitution. It ends up, and this is a key thing, that the chemical concentration of potassium and sodium are exactly opposite inside the cell compared to outside the cell. All right. So inside the cell, the potassium is very high and the sodium is very low. It's got also a lot of protein. And outside the cell, the fluid that's right outside the cell membrane, the sodium is very high and the potassium is very low. Now, this gets to the laws of nature, the forces of nature. It's because the sodium and the water and the potassium can cross through the cell membrane, nature is going to make them equilibrate. So it's going to make potassium come out of the cell, sodium and water go into the cell. Diffusion and something called osmosis together. If you don't do something about that, okay, you're not going to have homeostasis. Everything's going to fall apart, okay? So what you have is you have this what's called the sodium-potassium pump. They have about 1 million of them in each cell. And they use ATP, they use energy. They're like nano machine, and they're as we're sitting here right now talking, every cell in your body has about several 100,000, 1 million of these sodium potassium pumps, and what they're doing is they're pumping out three ions of sodium for every 2 ions of potassium they're putting back in. Now, this requires energy because you're pushing these ions against their natural way. You're pushing them back to where there's a high concentration, so it's against the gradient. And actually at rest, your body uses about 1/4 of all of our energy needs right now is just for those. For nerve cells, it's about 70%. So So there's one example of homeostasis. But now, remember I said we got the intracellular, now we got the extracellular body, the extracellular part of the body, okay? And almost everything else I'm going to talk about is that. The body needs energy, right? We need oxygen. We need glucose, so the body has to control that. You need to have enough of that, otherwise the body dies. You need enough water for cell function. If you don't have enough water, you get dehydrated, the cell shrinks, the proteins coagulate, and they don't work, okay? But and at the same time, you don't have enough water in the extracellular space, so you don't have enough blood flow, right? The blood pressure goes down, no blood flow, you're not feeding the tissue. So you have to control water as well, right? You need to control potassium and calcium. I mentioned the calcium. Potassium has a similar problem. Too high or too low, nerves and muscles in the heart don't work properly, and you die, okay? You need to control carbon dioxide and iron because they're very toxic to the body, so cells die. And finally, as another example, just the core temperature in the body. If your temperature goes too high or too low, the cell membranes don't work properly and the enzymes in the cells don't work. So you're left with all these things we just talked about: oxygen, carbon dioxide, water, glucose, potassium, calcium, iron, temperature, okay? Each one of these, if they're out of whack, you're dead, okay? So, you got all these problems you got to solve. And how do you solve them? You have to have a control system. How do you have a control system? Well, remember what I just talked about, the parathyroid and the calcium, and we talked about oxygen in the respiratory center. You have to have a sensor that detects all these things, all right? Any of these things, each of them. Then you have to have control logic. That information has to go to a control logic, or what I call an integrator, to decide, okay, is this the right? It's like a thermostat on your furnace, okay? Is this okay? Do I have to turn on? Do I have to turn off? Whatever. Do I need to put the air on? Whatever, okay? And then a signal has to be sent to an effector to do something about it. So as the example we've already given, in the parathyroid gland, the cell itself, basically on whatever the calcium level is, the signal it sends out is the parathyroid hormone. For breathing, you got the respiratory center in the brain that's detecting oxygen and carbon dioxide, and if it's not right, it sends a nerve message, down through the nerves to through the spinal cord into the muscles of respiration, so you start breathing. So that's how all that works. And of course, besides always having to change, this is dynamic. The gases are always changing in your body. Oxygen and carbon dioxide, sugar's going up and down, the blood pressure's going up and down. Even when you bend over and you get dizzy and you stand up, it goes away. There's a system in your body that's taking care of that. So all these things, so you're always making adjustments, and they all seem to know what they're supposed to do. Okay, and where did it come from? And remember, each one of these systems, not only is it irreducibly complex just to control it, but each one of these parameters has to be in the right range. Otherwise, you die. You could have everything normal. If your oxygen's too low, you're dead. Everything else could be normal, but carbon dioxide goes too high, you're dead. So there's all these systems that have to be under control.
Yeah, and it's definitely a life or death proposition, isn't it? You can't let anybody tell you otherwise. It's truly life or death, and you do need to look at that when you're studying the human body and organisms. Now, in addition to the production of continuous energy and the precise regulation of numerous interdependent systems and subsystems, as you've explained, life has another extraordinary capability that sets it apart from everything else in the universe. It can reproduce itself. And your amazing body actually has 2 chapters on how we go from 1 fertilized cell to 2 trillion at birth, and then around 30 trillion by the time we've hit maturity. You and Steve note that it's not just the number of cells that's impressive in this feat, it's also the number of problems the developing body has to solve along the way. Now, I know that's a big system of subsystems and there's a lot involved, but what are a few of your favorite solutions to the challenges involved in going from 1 to trillions of cells?
Oh yeah, you're right. It's truly amazing. And I had to go back and read all this stuff. You're going from a 1-celled zygote, and about 38, 40 weeks later, you got a 2 trillion cell newborn that comes out and is able to survive. And of course, in order to be able to do that, all the organ systems have to come online. So you got like 200 different types of cell types and all the organ systems, et cetera. But the 3 things that we wrote about, and the 3 things that I think that struck us for me first is, which is just amazing, is when the embryo starts, it's getting its what it needs, oxygen and sugar, et cetera, from the lining of the uterus. But eventually, and this is through diffusion, but eventually the placenta has to kick in. It's very interesting that, and fascinating to have this cooperation, because the placenta, which allows the mother to provide these things for the fetus, it actually is produced from part of the mother and from the embryo as well. So it's a combined tissue coming together. That's number one. The second thing is that although the mother can provide everything for the baby, right? There's just one thing that she can't do, and that is once the blood is going in from the placenta into the fetus or embryo, it's got to send out. It's got to distribute the blood itself. So there you are, right on time, about 2.5 or 3 weeks into the process. The cardiovascular system kicks in, the heart starts pumping. You got you got the arteries forming, and you got blood there, and so the embryo fetus can take over, at least do that part of things. And directly connected to that is another just incredible feat. And so what I need to start with is just to explain, and we have this in the book. It's also in the videos that we'll be doing later. So you remember how the heart works, okay? For us, all right. The blood starts in the left ventricle, full of oxygen, gets pumped throughout the body, goes to the aorta, through the systemic vessels. So you supply your tissues with oxygen, okay, and sugar, etc., right? And then the blood comes back to the right side of the heart, right atrium, right ventricle, gets pumped to the lungs. The lungs put oxygen in there, and then the blood comes back to the left side, and this is a continuous cycle. So the problem that we have with the fetus and the embryo is that the lungs aren't open, okay? And so you've got blood coming from the mother, from the placenta, that actually entered, and it's been oxygenated. Just to let you know that the oxygen level in a fetus is a lot lower than it is for us, for humans, for men, adults. So there's fetal hemoglobin. If I'm not mistaken, not only can it hold on to more oxygen, but can release more oxygen. You have a different kind of hemoglobin, as I said. But the blood's coming to the right side of the heart, and the problem is that it's got to get to the systemic vessels. How's it going to do that? Because the lungs are closed. What ends up, there's two shunts, right? Basically two shunts. There's one called the foramen ovale. It's basically a valve type of shunt between the right and left atrium. So a lot of the blood coming down from the head and neck into the right atrium for the heart will shoot right through that opening. Instead of going to the right ventricle, will go through that foramen ovale, go to the left atrium, and then from there to the left ventricle, and then it gets pumped to the body, okay? And then there's a second shunt that the blood is now from the right ventricle being pumped to the pulmonary artery, but the lungs are closed, right? There's nowhere for it to go. Well, there's a shunt called the ductus arteriosus. It's almost like a regular, as thick as a pulmonary artery or the aorta, and that's a passageway between the pulmonary artery and the aorta. So where the aorta is arching out, coming up over the heart to pump the blood to the tissues, blood from the pulmonary artery is actually going through there. So that's how the blood bypasses. But here's the problem. Okay, we got this. So you have to ask yourself, where did this come from? I mean, evolution made this happen? What kind of change could have made this happen? I mean, give me a break, okay? But here's the other thing. Once the baby is born, okay, opens the lungs, takes a big breath, starts crying, right? Has to take big breaths because the lungs have been closed, and because of the surface tension of water, the alveoli tend to stay close. So they have to take some really big breaths. That's probably the commonest problem for premature children. Babies that have respiratory problems because they're just not taking big enough breaths and opening the lungs. Yeah. Now you got the blood going to the lungs, right? But you got these openings. You got these ducts, these shunts. What's going to happen to them? Well, it ends up that because of these changes, that foramen ovale closes off by itself because all of the blood's coming to the left atrium, and it basically pushes that. It's sort of a little valve type of flap type of opening, and that closes and seals. Although 25% of people, when they get an echocardiogram, find out it's slightly open. It doesn't usually bother them at all. But you got this ductus arteriosus, which is like as thick as it's as thick as the pulmonary artery and aorta, right? It's like an artery, and what ends up happening is when the oxygen level rises, goes up high, it signals these smooth muscle cells inside that ductus to maximally contract, and it closes down as well. So not only do you have the system in place, but you've actually got the mechanisms in place for it to go back to what should be normal, outside, the newborn outside the womb. And this is just, like Steve says, this is phenomenal engineering. Okay. You're predicting, it's almost like landing on the moon and making sure everything works out fine and coming back. I mean, that's basically what's going on. And, of course, there's no explanation. It evolved. Of course, we know it evolved, but those are just three just amazing things. And, urge people to get the book and read it, or wait for our video as well to explain all these things. It's just amazing.
Yeah, fascinating levels of detail. And you do have to keep asking, can a stepwise gradual process account for this? We have to always remember that a Darwinian process cannot jump. It can only move forward slowly, in a stepwise fashion. And how do you do that when there's so many interdependencies, so many, interconnected systems that rely on one another? It really beggars belief. Now, in chapter 4, you recount the story of your granddaughter, Selena, suffering from bronchiolitis, illustrating how quickly even robust systems like respiration can be compromised. How does the body handle the challenge of bringing in enough oxygen while also getting rid of enough CO2?
Yeah, and this is a topic we actually, it's in, if you had a chance to see the video about engineered for oxygen, and sort of a bit of an overlap as we discussed, but basically, we're talking about the respiratory system. So you've got the nose and the mouth, you got the airways through the trachea, the bronchi, bronchioles, which go into the alveoli. All right. Then you got the chest and the muscles of respiration. So, and on top of that, what we highlight in the video is something that I'm not sure it's in the book too much about, but the thing is that the oxygen diffuses from the alveoli into the blood in the capillaries at a certain rate. And, as we just said, you need 250 milliliters a minute per oxygen while we're sitting there. And if you're active, well, 3,500. So the the actual surface area that the lungs need to get enough oxygen into the blood is actually about half the size of a tennis court. Okay.
Wow.
And if we just looked at if the lungs, and we point that out in the video, but if the lungs were just like spherical and they each have a volume, their total of volume of about 6 liters. If you looked at the surface area of that, the alveoli, which are tiny little sacs, which increases the surface area, it's like 500 times more than if each lung was just a big sac. So that's how the lung function. And we talked about before also, being active enough. You have to have enough lung function. What the volume of the lungs are, how much the air is moving in and out. But with activity, right, the brain tells if you notice when you're moving around, you get active, you start running, right? You start breathing fast. But where does that come from? I mean, are you thinking about that? I mean, the body knows what it's supposed to do, okay? And so at rest, you're maybe breathing 4 to 6 liters of air per minute. But when you start getting active, it goes up to maybe 40, 60. With athletes, it could go up to 100 liters a minute. And you have to have that lung capacity to be able to do that. And also, we're talking about oxygen and the release of carbon dioxide, but it's not going to help you unless the heart speeds up as well. So the same thing happens there. You have the sympathetic nervous system sends a message to the heart, and the heart normally at rest puts out about 5 liters a minute, and suddenly quintuples to 25 liters a minute. So we talk about that in the video. We also comment about this cascading problems, because even though the oxygen is coming in from the lungs to the blood, the problem is that the fluid component of blood oxygen doesn't dissolve very well there. So you have to have hemoglobin. That's the reason why you make red blood cells in the bone marrow, makes hemoglobin. The hemoglobin in your blood grabs onto the oxygen, travels out to the tissues and releases it. But then another problem is that hemoglobin needs iron. And we said iron is toxic, right, to the body. And so the liver monitors the iron level in the body and sends messages to the intestine that tells it how much iron to build, to bring in. So there's all these things going on. The question is, like, you can see all these interdependencies and control systems, et cetera. And you got to ask yourself, like, where did this all come from?
Yeah. Well, and I like how you point out in the book, you and Steve, that, for every problem you solve as an engineer looking at building something, you've now opened up, other lines of problems that themselves need to be solved. And that's where you get that interdependence and that interrelatedness. Is it's not just one problem to solve, it's 5, 10, 15 all in a row and all downstream from one another. And that's where you get the layers of complexity and design that are beyond a stepwise gradual process. Quite amazing. Now, I know we say the word amazing a lot in relation to all this, but your book also has chapters on the systems of seeing, hearing, balance, movement. Now, we don't have time to get into all of these. I encourage people to get a copy of this book. It's a very straightforward, concise read. So we're not going to jump into every class of evidence that you cover, but you're covering all of this even in a short 145 pages. You managed to demonstrate the myriad of engineering problems that must get addressed so that we can see, hear, and move. Now, as we wrap up, I want to talk about the process of condensing your previous book, which was Your Design Body. That came in at, I think, 500 pages. So very detailed in its review of all the different subsystems of the body. And that turned into this shorter one, which is about a quarter of the size. Now, what was the thinking behind having an abridged book, and who do you think it would be helpful for?
Yeah, well, this as we mentioned, this relates to the video. We were sort of asked to. We had a donor that really liked the original Your Design Body, and just thought that maybe we could scale it down a bit so it's not so overwhelming for some readers, and it is pretty extensive. But also wanted some videos, and it was a very interesting process for us talking about, because the book ties in with the videos as well. So the first video, which is out there right now, is engineered for oxygen. So we had to cover homeostasis in some way. In the book, we cover every aspect of homeostasis. We talk about oxygen and carbon dioxide. We look at sugar. We look at iron. All these different things. But everyone can relate to the heart and the lungs. I think it's life. It's life. Life affirming, life threatening if anything goes wrong with the heart and lungs. Cardiopulmonary arrest. I mean, they're two connected. So that's why we did that, and we didn't feel that we had to do everything else. We're trying to scale back. And then what we had in our book is something called Beyond Homeostasis. We got homeostasis, and so you've got the body managing everything, so you can concentrate on some more important things. Okay. And so, vision, people can relate to hearing, etc. So we get into detail on that, and proprioception, which is so important because it basically have these sensors in your muscles that are basically telling the brain how the tension in the muscles, but also tells them exactly where they are in space, because by telling them the tension in the muscle, it tells them the angle of the joint. So all those are very, very important, and so that's why we did that. And then the last part is on development, because that's so important as well. So it was a very interesting process because it's not like writing a book. And between Steve and me and the videographer and then the animators, we sort of had to write like a screenplay, and try to figure out, okay, what's going to be on the screen that they're watching while we're doing a voiceover, etc. And very, very interesting. A totally different medium to work with, and we just hope it works out. But that sort of it was the videos, but also drove the book, and so the two of them impacted each other. And I think we did a good job. I think Jonathan Witt helped immensely in editing down from 500 pages to 145. He did a great job. And I hope more people get it. And between that and the videos, that will help them. The two to go together.
Well, you have this comprehensive resource, Your Design Body, which has all the detail that one would want to expect to jump into. But then you have these two new resources that can help others who may not sit down to a 500-page book. And so I think it's great that you've produced these additional ways of learning about the body. Now, Howard, as we wrap up our discussion today, let's just bring it back to Darwin and evolution, just as your later chapter in the book does. You and Steve title that chapter, A Theory of Billions of Innovative Accidents. It begins with a review of the 4 causal factors of Darwin's theory: variation, heritability, natural selection, and, of course, the granddaddy, the big one, time. Lots and lots of time. Now, you do admit that the theory has a simplicity and an elegance to it that's, quite appealing for people. And that's kind of what's kept it in the fray for so long. It has an elegance to it, but when you get close as an engineer or someone who's studying these systems of the body as you have, you start to see that elegance unravel. That simplicity is a little too simple to match up to the design and the the prowess, the engineering prowess that is there in reality. And now let's not forget that life is always and forever a do or die position. There's no partially being alive. There's a living thing and a non-living environment around it that provides the set of problems that life has to solve to stay alive. And that equilibrium with the environment either means death or life. And there's only one way to go there. Now, what are some of the problems with Darwinian theory that you and Steve lay out, especially towards the end of the book, as you're closing this amazing tour of the body?
Well, I think that as you've already mentioned, the problem with neo-Darwinism, it doesn't really have a theory of generation. Okay, it really can't. It's all chance or random. Okay, it's just trial and error. All right, and I mean, engineers will tell you, that if you just do that, you're not going to get anything. I mean, they're using their intelligence to try to figure things out. It's hard enough for what they do, and Steve will tell you that the human body is much more complicated than anything that humanity has ever invented. So we're basically in this paradox of, as I said, if you go to a museum of natural science, you're going to see these bones, and you're going to see life, and it's going to say, hey, this just came from nothing. But then you go to a museum of science and technology, what are you going to see? You're going to see the design, the design, build, and test of all these inventors. You're going to see their equations, and you see all their calculations and their blueprints and all the things that didn't work. Like if you go to the Kennedy Space Center and you watch the rockets, going off, right? And we're supposed to be impressed with their intellect, right? The intellectual, insight in what they've done, right? And rightly so, right? But somehow something that's even more complicated than that, well, that just came about from random. So basically, you can't generate non-trivial innovations, which we're talking about, and that's about everything we've discussed already today. Okay, and not only from the cellular level, which and of course the total body level, which is what I'm involved with. Okay, and so the things that you need control. Okay, you need irreducibly complex systems. Each necessary that seem to know what they're supposed to do. Right. You have these coherent systems. Remember, right parts made and assembled right, doing the right things right at the right time. Okay, you have this interdependency. So in our video on oxygen, getting enough, engineer for oxygen, we comment that in order to get enough oxygen, you need the respiratory system, but you need the cardiovascular system because you got to pump it out, pump it to the body, right? You need the gastrointestinal system to bring in iron. You need the bone or the bone marrow to make the red cells, and you need the nerves and the muscles to work the lungs. But here's the point: all of these systems have cells that need oxygen, right? So how can they function? The lung itself is dependent on its own function. How can you if basically gradualism fails because the small steps don't work if the organism has to be alive each step along the way. Like you said, it's do or die. Okay. Here's a key thing that I've noticed, especially in the Darwinian narratives. Okay. First of all, evolutionary biologists tend to conflate explaining how a system or organ looks or what it does with how it evolved. It just says, it explains what it says and just it evolved. Okay. We have to remember that natural selection doesn't generate anything. It only preserves what comes about from random variation and genetic mutation. So this is a common error. People say, "Oh, evolution did that," or natural selection did. Natural selection doesn't make anything, right? You have to have the changes to get a new system that maybe get preserved. Okay, that's different. But natural selection doesn't make anything. If you understand, if I'm understanding neo-Darwinism properly. And finally, as we say in the book, neo-Darwinism is counterintuitive. I mean, it's hard to imagine how these systems came into being. If I'm not mistaken, I think I read somewhere that one of the evolution biologists complained that Michael Behe doesn't have a good enough imagination. That was the complaint. It wasn't anything against what he said, right? But that was one of his complaints. So I don't, nothing's ever changed. I mean, I was like 17 or 18 sitting in my science class and immediately saw this. I didn't, I never bought what Dawkins said. I mean, this reminds me of the Emperor's Clothes. You know, biology looks like it's designed, but it really isn't. Says who? Says you. Right? Go ahead.
Yeah.
I'm not gonna. You know what? I'm not going to risk my eternity on Dawkins. Okay, and that's the reason why I wrote this. I'm sure that Steve's involved with this as well. I want people to read, decide for themselves. I'm not telling them what to do. It's all up to them, right? But watch the videos, get the book, and you get the bigger book if you really want to dive down into it further. But really had enjoyed talking to you today.
Yeah. Yeah, thanks for your time, Howard, and unpacking these new resources that have come out of your design body. And let's do this again sometime soon.
Okay, nice talking to you.
Yeah. Now, if you're interested, listener, viewer, in your amazing body, studying it in a small group setting or just yourself, you can get copies at discovery.press. That's where to find copies of the book, discovery.press. And to watch the accompanying video series that Howard's been mentioning, you can go to secretsofthehumanbody.com. That's where we're going to have all the videos once they're all posted and they're done being produced. Secretsofthehumanbody.com. The first one is out and available, so you can definitely watch that one, but there will be others to come, and I'm excited about rolling that out in due course. That's secretsofthehumanbody.com. Well, for ID the Future, this is Dr. Howard Glicksman. I'm Andrew McDermott. Thanks for joining us.